Today we're diving into the critical material properties that every engineer should know. These properties determine how materials perform under various conditions, ensuring safety, performance and durability in engineering applications. Whether you're building bridges, designing airplanes, or even just choosing the right plastic for a water bottle, understanding these properties is super important. So buckle up, because we're about to unlock the secrets of the material world. Let's get started.
First up, we've got the heavy hitters of the material world: mechanical properties. These bad boys are all about how a material reacts to force. Think of it like this. You've got a big old steel beam holding up a bridge. You need to know it's not going to buckle under pressure, right? That's where strength comes in. It's all about how much force a material can take before it says, "Nope, I'm out of here."
Then there's elasticity, which is how much a material can bend without staying bent out of shape. Like a diving board, it needs to bounce back, not become a permanent U-turn.
Plasticity is the opposite. It's a material's ability to be molded into different shapes without breaking. Think Play-Doh, but for building airplanes.
Ductility is similar. It's how much you can stretch a material before it snaps. You want ductile materials for stuff like wires, so they can bend and flex without going kaput.
Hardness is a no-brainer. It's how resistant a material is to scratching or denting. Diamonds are the champs here, but for most things, you just need something that can take a beating without getting all dinged up.
Toughness is a material's resistance to, toughness. It's how much energy it can absorb before it breaks.
Now, imagine that bridge we were talking about earlier. It's not just dealing with one big force. It's got cars and trucks driving over it all day long, creating these tiny little stresses over and over. That's where fatigue strength comes in. It's a material's ability to withstand repeated stress without failing.
All right, let's crank up the heat and talk about thermal properties. These are all about how materials react to temperature changes. First up, we've got thermal conductivity, which is how easily heat travels through a material. Think about a frying pan. You want the heat from the stove to transfer to your food quickly and evenly, right? That's why frying pans are often made of materials with high thermal conductivity, like copper or aluminum.
On the flip side, you wouldn't want your house built out of copper. You'd be sweating bullets in the summer and freezing your butt off in the winter. You want materials with low thermal conductivity for insulation, like fiberglass or foam.
Next, we've got thermal expansion. This is how much a material expands or contracts when the temperature changes. You know those expansion joints on bridges? Those are there to accommodate the expansion and contraction of the bridge deck as the temperature changes throughout the day. Without them, the bridge could buckle under the stress. Understanding thermal properties is crucial in a ton of engineering applications, from designing engines and power plants to developing new materials for electronics and aerospace.
All right, let's switch gears and talk about electrical properties. These are all about how materials interact with electricity. First up, we've got conductivity, which is how easily electricity flows through a material. Think of it like a water slide. A material with high conductivity is like a super slippery slide, where the water or electricity just zips right through. That's why we use copper for electrical wiring. It's an awesome conductor.
On the flip side, insulators are like bumpy slides with lots of friction. They resist the flow of electricity. That's why we use rubber or plastic to cover our wires. They keep the electricity from zapping us.
Now, resistance is the opposite of conductivity. It's a measure of how much a material resists the flow of electricity. Think of it like the width of the water slide. A narrow slide creates more resistance, slowing the water down. Similarly, a material with high resistance makes it harder for electricity to flow.
Chapter 4. Magnetic attraction, magnetic properties. All right, let's get magnetic. No, not the kind that attracts your fridge art. We're talking about the magnetic properties of materials. First up, we've got permeability, which is how easily a material can be magnetized. Think of it like this. Imagine you've got a bunch of tiny compass needles inside a material. When you bring a magnet close, those needles will try to align themselves with the magnet's field. A material with high permeability is like having super responsive compass needles. They'll snap into alignment really easily. iron is a good example of a material with high permeability, which is why it's used in electromagnets. Now, coercivity is a bit like magnetic stubbornness. It's a measure of how difficult it is to demagnetize a material once it's been magnetized. Chapter 5. Now you see me, optical properties. Let's shed some light on optical properties, which are all about how materials interact with light. First up, we've got reflectivity, which is how much light bounces off a material's surface. Think of a mirror. It's got really high reflectivity, so most of the light that hits it bounces right back at you. On the other hand, something like black velvet has very low reflectivity. It absorbs most of the light that hits it. Reflectivity is important for things like mirrors, obviously, but also for things like solar panels, where you want to capture as much light as possible. Next, we've got the refractive index, which is a measure of how much light bends when it passes through a material. Think about a straw in a glass of water. It looks like it's bent at the waterline, right? That's because the light is being refracted as it passes from the air into the water. The refractive index is important for things like lenses, which use refraction to focus light. Chapter 6. Chemical breakdown, chemical properties. All right, let's get down to the nitty-gritty of chemical properties. These are all about how a material interacts with other substances at a chemical level. First up, we've got corrosion resistance, which is how well a material can withstand damage from things like rusting or oxidation. Think about a car that's been left out in the rain for too long. If it's made of steel, it's going to start to rust. But if it's made of stainless steel, which contains chromium, it'll be much more resistant to corrosion. Corrosion resistance is super important for things like bridges, pipelines, and anything else that's exposed to the elements.
Next, we've got flammability, which is how easily a material catches fire. You definitely don't want your house built out of something that's highly flammable.
Chapter 7. Weighing in physical properties. Now let's talk about physical properties. These are the characteristics of a material that can be observed or measured without changing its chemical composition. First up, we've got density, which is how much mass a material has per unit volume. Think about a bowling ball and a beach ball. They're about the same size, but the bowling ball is way heavier because it's much denser. Density is important for everything from designing airplanes to choosing the right materials for construction. Next, we've got porosity, which is a measure of the empty spaces or voids within a material. Think about a sponge. It's full of tiny holes that can absorb water. Porosity is important for things like filters, which use their porous structure to trap particles. Chapter 8. Sounds like a plan acoustic properties. Let's tune into the world of acoustic properties, which are all about how materials interact with sound. First up, we've got sound absorption, which is a material's ability to absorb sound waves rather than reflect them. Think about a recording studio. You want the walls to absorb sound so you don't get echoes and reverb. Materials like foam panels and acoustic tiles are great at absorbing sound. On the other hand, sound insulation is a material's ability to block sound from passing through it. Chapter 9. Going green, environmental properties. And finally, let's talk about environmental properties, which are becoming increasingly important in today's world.
First up, we've got biodegradability, which is a material's ability to break down naturally in the environment. Think about a banana peel. It'll decompose into compost in a matter of weeks, but a plastic bottle can take hundreds of years to break down. Choosing biodegradable materials is important for reducing waste and protecting the environment.
And then there's recyclability, which is a material's ability to be processed and reused in new products. Material Masterclass complete. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe for more informative content. See you next time.